So, good evening, everyone. Am I audible clearly?
Yes, sir.
Okay. So, welcome to week 5 of the live interactive sessions of Fundamental of Micro and Nanofabrication. The course instructor is Professor Susavan Avasti and Professor Sankar Salvaraja from ISC Bangalore. I am the PMRF teaching assistant, Vikas Pandey from IIT Jodhpur. This is a brief about me, the class link, the YouTube channel, and my contact details in case you need to contact me for any purpose. Okay, moving forward, uh, in this week, the things that has been covered are atomic layer deposition that was remaining from CVD and physical vapor deposition. Any questions or any doubts in this? Anyone, if you have any questions on this, you are free to ask. And during the process of the class, I will not be able to check messages. So feel free to unmute yourself and speak up.
Hello, I am having a query related to one of the assignment of the last week related to
Okay,
CVD.
okay,
So that is that the what decides the whether the precursor will go for reduction or for pyrolysis.
pyrolysis. Okay, yeah. I think
So
in one of the slides we covered this part. Yeah, continue. What were the
so
options?
so there were options. Let me read out. So the options were it is the type of reactor used,
Hmm,
the temperature at which the reaction is carried out,
hmm,
the chemical stability of precursor,
hmm.
and the presence of catalytic surface within the reactor.
Yes. So,
So I'm having queried that the correct answer what is the given is the temperature at which the it is been carried out.
yeah.
So if the reduction is always happening at the below pyrolytic temperature, sometimes it always I think it is happening below the pyrolytic temperature.
Hmm.
So how it is dependent on temperature because the stability is more important, right?
But stability, when we are talking about CVD, we
Mm.
are not concerned about the stability of the chemicals. Even if the like a chemical is less stable, but it
Mm.
reacts at a certain temperature. So,
Okay.
what will be the role of stability in that? Stability is
Because
something that we have to decide when we are choosing the precursor. But when
right.
we are, but when the reaction is happening, it is asking uh, what is the condition that will determine the reaction, and
Okay.
the determining factor for this, like whether it is reduction or pyrolysis, that will depend on the activation energy. We talked about this in the previous class also, right?
Mm-hmm.
So,
Mm.
and activation energy in case of CVD is like we said that we have very limited control over reaction in case of CVD, and that control is generally attained through temperature, right?
Yeah. Temperature and
Temperature,
pressure pressure. Yeah.
yeah, partial pressure or the flow of the gases.
Yes.
So,
Right.
and flow of the gases that actually will just increase the rate of reaction or decrease the rate of reaction or diffusion,
Mm.
right? But
Right.
whether the reaction will be happening and what will be the activation energy provided to it, it will depend on temperature, or in case it is plasma enhanced CVD or anything else. In that case, the specific activation energy will be provided by that agent. So
Mm-hmm.
the main factor that determines actually in any reaction is the activation energy that you are providing. That will determine the type, that will determine the actually that will determine sometimes even the need of catalyst. Like suppose there is a catalyst, and what the catalyst does, catalyst lowers the activation energy, that's all, right?
Right.
So even if there is a catalyst and we are not reaching the minimum attained minimum activation energy for that catalyst itself to work, Will it work?
Hmm.
Will the reaction happen?
No, it will not happen.
Not happen. That's why temperature plays a very important role when we are deciding which type of reaction it will be.
Okay. So it
At
does not mean that, for example, I'm working at lower temperature,
Mhm,
and even if it is below the pyrolytic temperature,
mhm.
the reaction will happen, right? So what this is what you are trying to say?
Yes, but temperature will play the role when what type of reaction will take place.
Okay. So, for example, if I'm not taking much time, then
No, no.
for example, I'm having a two precursor,
Yeah.
and one is having for example, I'm choosing a heptane, which is having a pyrolytic temperature at around 800 degrees centigrade.
Mhm.
So, if I am giving some catalyst and can be deposited with the lower temperature also,
Yes.
so then chemical stability is not that important, or what? I'm not
Chemical
still getting it.
stability will not be important, as well as when this question is in context of CVD. Okay,
Hmm.
where will you use the this catalyst?
Okay, matlab, this is just with respect to CVD.
Yes,
Yeah,
when
question is with respect to CVD. I got the
yeah,
point now.
yeah. So we cannot use the catalyst. If we are using the catalyst, the reaction will happen on the surface of catalyst, and the problem is that we want the deposition to occur on our substrate, not on the catalyst.
Right. But for reduction, I think two gases are required, right? Otherwise,
Yes,
there will not be reaction.
yeah. In fact, in most of this, either like we saw, na, different type of reactions that might happen
Right.
in case
Mm-hmm.
in CVD. If it is breaking out, like if a molecule is breaking out, then one molecule is enough, and sometimes even to break a molecule, some additional uh, gases are required, though they
Mm-hmm.
will not play any role. So there are in chemistry there are multiple possibilities, right?
Mm-hmm. Okay.
And for every possibility, there is a theory why it happens.
Right. Right.
So we have to see that.
Okay.
Yeah.
Okay.
Any other questions or
No.
anything? Yeah. Okay. So let's move forward. So, like in the previous class, also, I said that after uh, there is a special type of CVD, that is atomic layer deposition, in which why we are calling it a CVD or a PVD or physical vapor deposition. The difference is very simple. When the material that you want to deposit, you have that material prepared perfectly in the chemical composition you want. It is a physical vapor deposition. That is just you are changing the state or changing the uh, phase of the material and depositing it. Whereas if you have some chemical reaction that like there are two or three or multiple spaces that are reacting and forming the material that we want to deposit, then it will be called as CVD. That categorization is clear to everyone.
Yes.
Yes.
Okay. Okay. So, and when we are talking about atomic layer deposition, if you see the equipment and all, it will look very much like in case of CVDs, whenever we are talking about there is temperature involved in these things. So if you see the atomic layer deposition, it will look like a PVD system when you see PVD and these things. But it is CVD since reactions are taking place and then the deposition happens. So the sorry, the name itself suggests that it is atomic layer deposition. That means deposit materials one atomic layer at a time. And when we are talking about atomic layer, that means it will be even lesser than nanometer. It will be generally in terms of angstrom, some angstroms. It is depositing one layer, like one atomic layer at a time. So very precise, but as it can easily be understood that if we are depositing one metal atomic layer by one by one, it will be very precise, very good, very smooth, conformal, but very slow. And it operates at low temperature, unlike the other CVD method. And that is why This is something quite commonly used in case of flexible electronics, where people are using. We talked about in the first class. There was some topic that we covered. What are the different kind of substrate, and we said that these plastic, PET, and these Krypton, these substrate have limited uses. But ALD is something like we cannot put plastic or Krypton in 1000 or 1100 degrees Celsius. But since ALD is operating at a very low temperature or like room temperature, we can even use plastic and glasses for the coat to coat them, as well as it is effective for very high spec ratio structure. Like suppose that in the previous one topic we are saying that in some cases such structures are already made, and then we want to coat it, and we want it to be conformal, like the material that we want, that should deposit uniformly. But that is not the real case that happens. What happens is that it might deposit here, it might deposit something like this, the corners might be left, or there can be some over deposition here. Such things are very common. But since here in the ALD, one layer by one layer is being deposited, it is very conformal, very uniform. It is even very effective when we have something very high pillar like nano pillar or any such structure. Even it can coat it very easily. In case of so, how is it a bit although it is also a CVD, but how is it different from the normal CVD we have talked about? So in case of CVD, there was continuous flow of precursor, and reaction was it is like precursors are coming, reaction is taking place, the byproduct are going out. At the same time, other reactants are coming. Like that is a continuous process. But when we are talking about ALD, it is a sequential process. One one step completes, then the next step, then that step completes, then another step. So it is sequentially exposed to precursor, generally two precursors, A and B, and that leads to self-limiting reaction at the surface. So it is not that continuous deposition is to be done. One deposition or one layer deposition, then we like then we take time for other processes. We will see later, and then the next layer. So it is sequential. It is not like one layer done, next layer, next layer, next layer. So that is why this is slower, but step by step, and as well as sequential. So where is it typically used? It is generally used for oxides, even metals and nitrides, sulfides, and phosphides. So as we said, we have since it will be slow, one layer, so we know the atomic layer, like whatever. Suppose that you are depositing Al2O3. Okay, you know the thickness of the Al2O3, and that's why based on that we can very precisely calculate or very precisely know how much deposition has been done. So very precise control, unlike other method where we were in CVD, we were not able to understand what is the thickness, and that also in the process we were not able to check. In the case of ALD, during the process itself we can check how much deposition has occurred, because it is very sequential, layer by layer, like that, very consistent across complex surfaces. So what is the process? It is like we have a starting surface, clean starting surface. So we have some bonds there. Then one precursor is introduced. That precursor will bind to the dangling bonds on the surface, and then that precursor is purged out. So now we have one single layer of one reactant, like that is precursor one, or the material or the uh, reactant one. Then we put the precursor two, that is the reactant two. Then it will come, it will react, and then again it is purged. Now these two materials in their capability will react on the as per the optimal conditions we are providing, and then we are purging. So one layer is formed, we are leaving that as it is, and then again this surface is ready for the next deposition. Now no unreacted, like in case of CVD we had some unreacted spaces always present, they were coming continuously, but in this case one first material comes, whatever adsorption has to occur, that will occur, then it will be purged. After that another material or another reactant that will react, and then extra reactant will be purged out, and then this process will be repeated again with the precursor one purging precursor two, like this. Okay, anything till here? Any questions till here? Anyone?
No, not from me.
Okay,
Here.
so let's move forward. So the process steps are like I discussed, the precursor A, chemijobs. When we are talking about chemijob, that means it is chemically binded due to the dangling bond. You might be remembering from your intermediate that chemijobson, what is chemijobson, what is physijobson. It is a chemical reaction based thing. It is being chemijobbed onto the surface, forming a self-limiting monolayer. That means it will be like covering the whole surface as a monolayer, the precursor one itself. Then excess precursor is removed. That is why there is no reaction happening in the vicinity around it, because both of them meet only and only on the surface of the wafer that we want, nowhere else. No outside reaction is there. It is completely removed. Then the precursor 2 is introduced, and that reacts with the chemijob A, completing the layer of the desired material. Then this extra whatever material B is there, that is also removed, and as such we are getting one layer. Here one very important thing is the growth per cycle. How much growth or what is the thickness of the one monolayer? Like in case of Al2O3, if we talk, it is 1.07 angstrom per cycle. That means in one this process of precursor A purging, precursor B purging, this process, this deposits 1.07 angstrom per cycle. So if this process takes say 2 minutes, okay, or 120 seconds, then just to deposit 1 nanometer, how much time it will take? Anyone?
Mm,
Yes. Yeah, Ajit, you are saying something.
Uh, no, like just calculating. 1 angstrom is 10
10 to
raised
the
to
power
minus
minus 10. Yeah,
minus 10. So if you have to deposit 1 nanometer, right?
yeah, 10 to the power minus 9.
So 10 times of that.
Yeah. So just to deposit 1 nanometer of Al2O3, we will require around 20 minutes,
Yes,
like 20 minutes of
correct.
deposition.
20 minutes.
Yeah.
Yes.
Whereas if you compare it with CVD, in 22, like in 1 hour, generally we are getting 200, 300 nanometer of deposition, sometimes even in microns. Even if you compare it with PVD, other PVD deposition like thermal and sputtering. We will be covering those. Even in that case, this time is well enough for some good thickness. Okay, like 50, 60 at least nanometer. So this is slow, but precise. Okay, so how like there are different uh, kind of this sorry, ALD systems. Okay, so you the question arises that in case of CVD, what was the source of activation energy that we were using? Yes, anyone?
What's the question?
What was the source of the activation energy we were providing in case of CVD?
Temperature.
Temperature, right? But here we are saying that it is a low temperature process. So there must be some uh, activation energy, like we must be providing some activation energy for the reaction to happen, and that is through a RF plasma, RF plasma source in the vicinity of the wafer where deposition is to be done. The plasma is being created that provides the energy for this reaction to take place. Okay, here like an example of deposition of Al2O3 is shown. So AlCH3 uh, in gaseous form is inserted, and then it will adhere to the surface of the wafer. Then H2O is inserted in after purging this, and that also in pulses so that complete reaction takes place. Once the complete reaction takes place, and along with the byproduct, the extra H2O is removed, and then we will have Al2O3 monolayer forming on the top. Okay, and this is repeated multiple times to attain the number of single molecular layers we want. Fine. Okay. So, what are the things that we need to optimize when we are working with a ALD system? One is the dose time. It is not that we put the precursor A and it will get chemized out at once. So it must not be too short. Otherwise, the monolayer will not form. As well as like if we are putting it for too long time, what will happen that we will be wasting time for a already slow process. Okay, so dose optimization is a very important material consideration to be uh, considered. How for how much time we have to put the precursor, sorry, the precursor for the complete chemabsorption on the surface. So optimal dose is important. Second is the purge time. If we have to remove the extra material, that time also is very critical. First is the purging should be for adequate time to remove anything that is extra. And second problem is that if we are not removing this, what will happen? It will be like CVD. A lot of reactions will be taking place, and we will not get the monolayer we want, and no uniformity will not be there. So both dose time and purging time both are very important. How much we are doing it, and it should not be like we are purging too much that even the chemijob precursor actually moves out. It should not be like that. That we are pulling out a lot of precursors, like trying to pull out everything, and actually it also comes out. That should also not happen. Many times the precursor are gases. So the optimization process is to identify the optimal dose and purge time for both, and it must may not be same for both the material precursor A as well as precursor B, so that the saturation region, uh, the saturation regime of ALD is there. That means the reaction is happening on its optimal rate. Okay, so that we have uniform repeat and repeated growth. Right? So what are the advantages? This is taken from this website. They make ALD system. So they have provided some images. So you see, if it was a CVD system, and this the scale is actually quite low. I forgot to put the scale here. It's quite low in terms of microns. Okay, and sometimes even in nano, if you find, see the coverage. It is almost the same thickness here, what it is on the side walls, which is not possible when we are doing a CVD or PVD process in common, like in general sense. So it is very good in coating deep trenches and complex geometry with uniform thickness. Okay, then it is independent of the gas flow dynamics. So there we had to see whether it is turbulent or like we were seeing Reynolds number and everything. Here that's not relevant. It is very ideal for precise thickness control and coverage, such as semiconductor devices and coating on 3D structure. 3D, or when we are talking about 3D, we are talking about MEMS structure. And one more advantage, it is compatible with plastic or flexible substrate. Then there is one more factor that can affect our deposition, that is temperature effect. Although it is a low temperature process, that means we are not going to very high temperatures, but temperature will certainly have an effect, since uh, it is one of the factor that facilitates the reaction. So if this whole process is being done at a very low temperature, lower than our the optimal temperature at which this will occur, then precursors will condense on the substrate, and that's why they will form multiple layers. Instead of, if they are just getting chemised, they will form a monolayer. But what if they condense on the surface? In that case, there will be some patches or like non-uniform or CVD-like growth, as well as there will be insufficient reaction, because uh, if we have multiple layers and the next precursor we are giving in the amount that it will react for do reaction for one layer only, so some reactant, some precursor A will remain unreacted. Then what if it is being done at a very high temperature? So in that case, some decomposition can happen without without bringing the precursor to, some reaction might start happening, like the precursor itself start decomposing into different elements and its molecules. Okay, as well as temperature have role on the chemistry option. Okay, so due to this temperature, the high temperature, this molecule actually become, you say it becomes too active or excited, and it will leave the surface where it was supposed to adhere to. That's why we will not get uniform and repeatable results. Just a minute. Yeah. So, uh, am I audible?
Yes, yes.
Okay. Then one more problem can occur, that is non-ideal nucleation. That is, sometimes less nucleation occurs. The precursor is not sticking on the substrate, leading to slower initial growth because the first layer has to anyway stick on the surface, right? On the dangling board. Later on, it is the same molecule, it will easily stick or like that. But the substrate, like it has to adhere to the substrate. That might not happen. And one example is titanium nitride on SiO2. Or it can be that like there are a lot of bond and all the molecule rush to nucleate over it. And instead of one layer, we are getting multiple layers at first. The first layer we are talking about, the starting of the seed layer. Okay. So next, if we have some less nucleation kind of condition happening, then it will lead to slower initial growth and later on it will be linear because later on other like temperature, plasma, and these things are the deciding factor. This is when we are talking about nucleation, we are talking about the interface, the first interface of the substrate and the precursor A we are talking about. If there is more nucleation, there will be very uh, fast initial growth, but later on it will again become linear. Then how to address this? To address this, we have to know the type of substrate and the like the interaction. We have to already know the interaction between the substrate and the uh, deposited film or the precursor that we are taking. And according to that, we have to adjust the initial or the starting growth. Once that is done, later on, that is linear. Okay. So how do we compare this to CVD or PVD? CVD we have covered, PVD will be covering next. Okay, growth rate. If we talk about the growth rate, it is 0.1 to 1 nanometer per minute. Okay, it depends on the thickness of the molecule that we are talking about. Whereas if we are talking about CVD, it will be 10 to 100 nanometer per minute. And if we are talking about PVD, it will be 100 to 1 micrometer per minute. Conformality, ALD is having the best coverage, 100% coverage. CVD, it has medium and it is transport dependent. PVD has low coverage. What materials can be deposited? Oxides, nitrides, sulfides, metals, and elements. Almost same for CVD, and PVD is mostly preferred for metal elements. Alloys also. This is unique thing. Alloys can only be deposited using PVD. CVD and ALD are not suitable for alloys. As well as some dielectrics, not all, like oxides and nitride, can be deposited using PVD. But this is the cheapest and easiest, like requiring some less effort because here we have the material and we are directly depositing. In case of CVD, there are some other factors like we have some complexities. Although it is also cheap in the sense that you just have to have a tube furnace and all things. But temperature is an issue. It requires very high temperature. In ALD, it can work in different wide range of temperature, and that also generally in this case that whole system or whole chamber is not to be heated. Only the wafer area where the reaction will actually take place, that has to be heated, and it works fine. In case we are going for high temperature system, anyway it works even in low temperature. In PVD, the advantage is low temperature. Growth mechanism in case of ALD is self-limiting. In CVD, it is continuous, as well as PVD, it is continuous. The direction of growth is isotropic, that's in all direction. CVD also is in all direction. In PVD, it is line of sight. So if this is something that is even used for advantage in some of the processes, like people cover the part that we don't want the deposition to happen with a simple physical mask like tungsten or steel mask. Okay, in some like where you don't want very small feature size, there you can go for such structure, such things also in PVD, which is not possible in case of CVD. Okay, so any questions still here? Any doubt or anything?
May we know the like general temperature ranges of CVD and PVD?
CVD, like we discussed in the previous class also, that it is generally going from like starting from 300, some reactions take place from 300
Mhm.
to around 1100 degrees Celsius, 11 to 1200. Like most of the furnaces I have personally seen or encountered, they are
Okay.
going till 1100, 1200 degrees only.
Okay.
Yeah. And in case of ALD also, you can go like 800, 900 degrees since it is plasma enhanced. So certainly the same reaction can take place at a lower temperature, right?
Mm.
In PVD systems also, there are some depositions like improving the quality of deposition. Sometimes we go for temperature like 600, 800. In sputtering, we have used 650 degrees Celsius we have. Okay. In thermal also, we go for 100, 200, even 400, 500 degree. Okay. And anyway, thermal itself is a hot process. It actually, the material goes to evaporate. Where metals are evaporating, you can understand how, like, what is the temperature range. It must
Mhm.
be above 1000, like gold and silver, everything you will see evaporating with your eyes. If you see from the flap, you will be able to visualize those. So those are also, if we are in PVD, we have actually two different sects, we can say evaporation and sputtering. Okay.
Mm.
So evaporation, like we are evaporating the materials, uh, it will certainly go to high temperature. In sputtering also, sometimes we are going, not the material is not heated, but when depositing, the wafer is heated so that good adhesion, we get good adhesion, and the molecules easily, the sputtered molecules easily adhere to the surface.
Okay. In sputtering, wafer is heated.
Yes, sometimes.
Sometimes. Sometimes.
Yeah,
Huh.
not
Huh.
not
Not
always.
all times. Okay. Okay.
Yeah.
Yes. Okay. Thank you.
Okay. Any other questions from anyone? Yes. Okay. So let's move forward to our next topic, which is physical vapor deposition. Okay. So uh, as we have discussed earlier also, chemical vapor deposition, where the exact thing that we want is not available. What is available is two different reactants that react and form our material that we want to deposit. But in case of vapor deposition, we start with the solid material source. we convert it into vapor and then deposit onto the substrate. So this is, in crude sense, a simple change of phase from solid to vapor and then again to solid or thin film. So first thing is, we have to have the material pre-prepared. It can be prepared by any chemical process, and then we have to have it with us. And when we are talking about microfabrication and these things, we have discussed about the purity of materials and chemicals. That is very important. Okay, so here also, whatever material we are starting with, we have to start with it, a good quality, very good quality of like starting material. We cannot say it as a precursor. Like in case of sputtering, we are mostly calling it as target. Uh, and in case of thermal, we are directly like putting metals and okay. So what is the application that we can do with this? One is metals. This is most common. Then silicides, nitrides, and polycrystalline thin films. Here, like we saw CVD, and in that case also we saw MOCVD or molecular beam epitaxy and these things, where even the crystal orientation is controlled. That is not possible in case of PVD, since it is we are depositing just a material over other. So here, molecular level or lattice level matching is not possible. Then optical films like anti-reflective coating and dielectric mirrors, these are made using PVD method. Low quality dielectric and semiconductor, but sometimes needed for certain applications like you just have to cover, you just need for passivation and these things, you can go for PVD. So, if you have to, you need some very good quality like get dielectric and these things, then PVD will not be the preferred one. Then in that case, CVD or ground oxide is used. But one key parameter is there in case of all the PVD system, that is high vacuum. High vacuum environment is used for effective deposition. And we will see when we are talking about vacuum, actually throughout the world we have different units of pressure. Okay, so whenever we get systems or whenever you encounter systems, you will hear different kind of pressure units. So one atmospheric pressure is 760 torr, or which is equivalent to 1000 millibar or 10 to the power 5 Pascal. Okay, and these are the normal pressure range, one atmospheric pressure range. Okay, when we are talking about vacuum, that is having lower pressure, air is removed from uh, our system. So a low vacuum, or the simplest form of vacuum, is something around 1 millibar, where we have internal pressure in our system or chamber around 1 millibar. That is considered a low vacuum. Okay. Then we have something called as medium vacuum, that is 10 to the power minus 3 to 10 to the power minus 1 millibar. So can anyone tell 10 to the power minus 1 will be a stronger vacuum or 10 to the power minus 3 will be a stronger vacuum?
10 raised to minus 3 will be more vacuum.
More vacuum. And why is it so?
Because it is smaller than 10 raised to minus 1.
Yeah, so smaller, how smaller is better?
Because smaller means less air inside.
Less air inside, so we have less pressure being exerted.
Yes.
And to sustain this less pressure, because if there is less pressure inside, outside pressure is too high for it to sustain. So the chambers that have to be designed, they also have to sustain such difference in pressure outside and inside. Okay, so that's why you will see that generally the PVC systems have very thick steel structures and all multiple structures to sustain such vacuums. Then comes the high vacuum, that is 10 to the power minus 6 to 10 to the power 10 to the power minus 4 to minus 6 range. And this is the typical vacuum ranges we use. Even when we use here at Jodhpur, we use this. In sputtering, we are going 2 into 10 to the power minus 6 range. And for thermal also 3 or 4 into 10 to the power minus 6 range, around that. Then there are very high vacuum systems, like if someone is familiar with STM imaging and all, in that very high as well as ultra high vacuums are used. STM 10 XPS, they use ultra high vacuum systems where we are going 10 to the power minus 7, minus 9 millibar, and more than minus 9 millibar also. So these are the pressure that we saw, but how these pressures are attained. And this is something that will, if you are encountering any such system, any PVD system, you'll spend most of the time making the vacuum. The real deposition or the real work is less, but most the maximum time that is utilized is to create such high vacuums. Okay, so how these are made? These are made using some vacuum pumps. So starting with a simple oil-sealed mechanical pump, which operates in the low to medium vacuum range. That is 10 to, it can go up to 10 to the power minus 3 millibar running it. Okay. Then we have turbomolecular pump and cryo pumps. We will not go deep into its working and all. If someone is interested, you can see they have a lot of different working. Cryo pump, like it works with liquid nitrogen where it freezes everything. And okay, these are used to achieve high vacuum. So, but with mostly it is like that. Okay, we will anyway cover that. Then we have iron sputter pump or titanium sublimation pump that is used for ultra high vacuum. There are different kind of pumps that are used, and generally for these two pumps to work, it is not that you start with a iron sputter pump and directly create a vacuum of 10 to the power minus 9. It is generally done that larger molecules or at first large amount of gases are removed from by some crude pumps like oil sealed mechanical pump and this. And once we have reached 10 to the power minus 2 range or something like that, then we go for turbomolecular pump, and then it reaches to 10 to the power minus 6 minus 7 range, and then ion sputter pumps are used to go to minus 9 minus 10 to the power minus 11 millibar sometimes. So there can be two pump system or three pump system for high vacuum and ultra high vacuums. So it is not that if we have to work in ultra high vacuum, we directly have a ion sputter pump. That will not work. It is generally done sequentially. One pump for reaching till some pressure range, then going below it, then going below it, because these have limitations that they cannot handle a large amount of gases. So if you are starting them at higher pressure, they might not work, they might get damaged. Okay, so whenever we are talking about PVD system, first thing is that we have to deal with vacuum pumps to create vacuum, because we need very high, like high to very high vacuum. Fine. Any questions still here?
No questions.
Okay.
No question.
Yeah. So next, there are two ways we can do PVD. One, and the simplest is evaporation. Okay, it's simple. We have a material, like suppose that you are going to deposit aluminum. You heat it to such a temperature that it evaporates, and you deposit it over a wafer. So it evaporates and deposits. Okay, and why is it done in why, if it is simply heat it and deposit it, why to do it in a vacuum chamber? The thing is that so that there is no collision of material molecules. This straight line of sight deposition can occur. Okay, then we have seen that high vacuum is required. It has two different reasons. One is there should be no chemical reaction because the material is already there. But since we are evaporating at a high temperature, some reaction might happen. If there is an oxide, there is nitrogen, something like aluminum oxide or aluminum nitride might form. We don't want that. We want aluminum to be deposited as such. So for that, we want to remove all contaminants, all chemical contaminants. That includes the air. Okay, that is one of the reasons that we do this. The second and the most important reason is to reduce scattering. The molecules of this evaporating material may collide with our environmental molecules, and as such, residual gases and environmental molecules. So we have to reduce that. We don't want that to happen, and that is why we are using high vacuum, so that minimal such interaction or minimal such uh, collisions occur. Okay. In this case, it is suitable for metals, and it is one of the most common ways where how metals are deposited. Some semiconductors are even deposited. One of my junior was recently like trying to deposit, I think, indigo. Indigo is a semiconductor, right? So he was trying to deposit indigo using thermal, and he was successful. Okay, so some semiconductors are even deposited. You will have to optimize properly. Okay, but generally we don't get high quality dielectric or epitaxy layers are not possible here because it's not like it. There is very least chance that some epitaxial growth can occur, and even if it occurs, it will occur like that happening throughout the wafer is very rare. Okay, so in this concept, one very important thing is mean free path. Uh, Anyone aware with this term? I think most of us have studied this, right? Anyone who knows what is mean free path? Hari, yeah, yeah, Amrish.
Yeah, it's the path the electron travels before it goes to collision.
Yeah. So in this case, we are talking about any kind of molecule
Any kind
or
of molecules. Yeah.
yeah, molecular species. So it is the average distance a molecule will travel without getting collided. In simple terms, right? So we want this mean free path to be large. Why large? Because suppose that this is our material kept in a crucible or something, and we have this wafer, and they are separated with a, at least there will be some separation. Otherwise, it will just stick to it and will not get its film. We generally want its film, and that also uniform. Okay, so if we just dip inside it, it will not work. So we will need some distance, say 10 centimeter. So in general, we want that the mean free path of the molecules that will evaporate from here should be more than 10 centimeter. Then only this deposition will occur. Otherwise, they will collide with each other and we'll see very uniform, non-uniform patches. Okay, as well as contamination will occur due to the collision of some other species. That's why we go for high vacuum. That means having longer mean free path and line of sight deposition, as well as efficiency and uniformity in the deposited film is there. And the next thing is impurity control. This is whenever we are talking about this field itself, it has to be like we have to deal with it with a lot of purity. Everything should be pure, clean, and such. Small contamination can have such roles that we cannot even imagine what uh, what electronic effect it might create, and what if a chip you are making and that is being used in say on a space station and that fails, and if that fails, even to correct that, uh, like just due to some contamination, that whole thing fails, and if it fails, a person have to go and repair, and that will take years for that person to be stuck. Like at present, Sunita William is there, and right there. Okay, so even a single contamination can have long-term effect on our devices. That's why it has to be controlled at each and every point. So contamination, increasing the mean free path and quality of material as well as uniformity will increase if we are going for high vacuum. Okay.
Uh,
Yes.
one, one question,
Yes. Yes.
Vikas sir.
Uh,
In CVD,
hmm.
like how do we measure the thickness of how much we have deposited? So
Okay.
in CVD, like we or in ALD, we know, right? Ki one layer deposited, so 1 angstrom deposited.
Mhm.
But in PVD, is it time based? For example, I run this PVD for 10 minutes, then this much thickness, 20
Yes.
minutes, this much.
Like there are different methods we have discussed earlier also. Uh, the one method is like ellipsometry, especially for if we are talking about this one SiO2, and this ellipsometry is one of the common one where a light is reflected and all. Okay, that is one technique. When in case of PVD, what we do is that what we generally do is that for optimization at first, in some cases we have this crystal monitor. Okay, piezoelectric crystal monitors are used where uh, the deposition is happening. That same deposition will happen on that also. Okay, and as the deposition happens and we know the mass density of, say, suppose we are depositing gold. Okay,
Hmm.
so we know the density, so we feed the density, what is the density of our gold or whatever material we are going to deposit, and then on this piezoelectric what do you say sensor, that material will also get deposited along with it, like that will be kept along with the uh, our substrate, and with that its mass will increase, and as the mass increases it will sense how much deposition, like due to that weight, how much deposition is happening. And then later on also, once this is during the process, right, after the process also we are measuring either by using like we are putting some strip over our as I said, this is something where we can put uh, something over it, over our wafer, and that will cover, like that will not let the deposition to happen. Okay, so we are covering it, and later on we are using profilometer to determine the thickness. That simply is a tip that moves, and as it you are able to see my hand.
Yes, yes, yes.
Yeah. So like suppose that this is the complete wafer, and we have a deposition that happened in this side. Okay. So we covered this area by say a metal structure or a Teflon structure. Okay. A sharp Teflon structure. So we have a sharp interface here. Okay. Here deposition has occurred. This side no deposition has occurred. Okay. Then we go to profilometer, and there is a tip that touches this and slowly moves over it. So it will encounter this hill kind of structure, and it will show you how much is the thickness. So we know the thickness. For the surface morphology, we go for AFM. Even we go for SEM, TEM. There are different, a lot of characterization techniques used for the type of deposition, quality of film. But during deposition thickness, like there are limited ways. Whereas if we are talking about CVD, there is almost no way that we can do it. So the best way is that later on we check using any of these characterization techniques. Clear?
Okay, okay. Thank you.
Got it? Yeah. Okay. Now, next one concept is that there is arrival ratio. That is the ratio of the desired material atom to impure atoms during deposition. Whatever we may try, there will be some impurity that will come. Okay. So this arrival ratio, we have to get high, very high arrival ratio, almost like 0.999. Like if we are taking the arrival ratio, the perfect one to be 1. Okay. Not 1, sorry. Material to impurity, that is impurity should be 0. So it almost to infinity. Okay. So it should be very, very large. This ratio should be as large as possible. That is, desired material is very high compared to impure metals. So higher vacuum increases this arrival ratio, and thus we are getting pure films. Another factor is evaporation rate. Okay. This will depend on the vapor pressure of the material. That means here we are talking about vapor pressure of a solid once it gets heated. Okay. And heating here, we will see, I think heating can be done using different methods. When we are talking about evaporation, most common method is reactive heating. That is, we have a, I think I'm not, we have a small, generally tungsten is a very hard substance. So we have small boat kind of, very small strip kind of structure with small central crucible. So this is the side view I am talking about. Okay, this made of generally tungsten. Okay, and we are putting our material here, and we are connecting it to current source outside through transformer and all, and we are giving high current. And high current means really high current, like say 100 to 120 amperes. And you must be aware that in our houses, whatever appliance we use, 32 ampere is something like, it's the highest rated uh, switches we use are 32 amperes. We don't go above it. Anyway, that is something, it rarely happens. 32 ampere is something that rarely happens in our uh, homes. But here, 100, 120 is the normal one. Sometimes we are even going 180, 200 amperes. And then, due to this current, this whole port glows, it gets heated, and it melts this and it evaporates. Okay. So, during that time, this, how much is the vapor pressure of this material and the temperature at which this is happening, this will determine the evaporation rate and as such the deposition rate also. Vapor pressure has exponential dependence on temperature. So vapor pressure is determining the evaporation rate, and the vapor pressure is dependent on the temperature, and temperature not of the chamber. We are talking about the temperature at which this material is, that is getting evaporated or melted, like melted and then evaporated. And some materials are directly sublimating, so in that case they are not changing its phase, like chromium no chromium yeah, chromium sublimates, I think. Yeah. So this vapor pressure will significantly vary with temperature, and some materials like tungsten, they require very high temperature. So here I am saying that it's a tungsten board, but what if we have to deposit tungsten itself? In that case, there are alumina boards in which tungsten is kept, and it requires very high temperature, and uh, we have to give adequate temperature for the evaporation for the materials like tungsten, as well as chromium also requires a lot of temperature, and nickel also requires. Okay, so and the optimal pressure range for this whole deposition to take place, this deposition takes place in the range of 10 to the power minus 6 to 10 to the power minus 2 torr or millibar we are talking about for effective deposition. The lower is better in case of evaporation. So we have to go to high vacuum, okay, and we have to maintain good vapor pressure. So as the vapor pressure will increase for the metal, the vacuum will degrade because there is some material that is getting there. So we have to maintain a good pressure as well as we have to maintain a good vapor pressure. So we have to make a combination of these two. So what is the advantage in this whole process is that, are you getting it, everyone?
Uh, did you say as the material will get deposited, the vacuum will get increase?
No, will
Will
degrade.
decrease. Will decrease.
Yeah, will degrade. That
Uh,
means since the like suppose that we are working at 5 into 10 to the power minus 6 millibar. Okay.
hmm,
So
hmm,
once we start, like we have not started any kind of deposition, everything is it. At present, we are just making the vacuum. Now we have reached this pressure.
hmm,
And if
hmm,
we start melting aluminum, say,
hmm,
so since aluminum will increase, like aluminum will exert some vapor pressure
hmm.
in the chamber. So
Okay.
you will observe that it will actually degrade, like say it will reach
Mhm.
8 into 10 to the power minus 6 millibar.
Okay.
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 So pressure will increase a bit. Okay.
Hmm.
So we have to maintain that the we have to maintain a good vapor pressure for good deposition, as well as we have to maintain good vacuum for uh, longer mean free path. It should not happen that once we start depositing, it reaches to 1 into 10 to the power minus, like 2 into 10 to the power minus 1 millibar. In that case, the vapor pressure is good, but
Hmm.
there will be a lot of collision and the deposition might not happen. So we have to take care of these things, that there should be a balance between both of these.
Okay. But like once we have created this vacuum
Hmm.
and we have started depositing, uh, like inside pressure will increase, but then do we again on the vacuum pump to remove that
The
inside
vacuum pump is kept on throughout the deposition.
throughout the deposition?
Yeah, it is never once the like it's the whole process starts with switching
Hmm.
on of vacuum pump, and the last thing to be switched off is a vacuum pump.
Okay. Okay.
The first thing to be switched on when the system starts is a vacuum pump, and the
Hmm.
last thing also is a vacuum pump that is switched off. So throughout the process, vacuum pump remains on. Everything, like, we have to, sometimes we might close the valve a bit, not
Hmm.
completely. The
Hmm.
outlet we can close somewhat, so that the pressure that we want is there. Like, it is
Hmm.
not that it is sucking everything out and we are not getting adequate vapor pressure.
Hmm.
So sometimes we have to adjust the valve, but overall it will always be on.
Okay. Okay. Like I was just thinking, otherwise it will remove the aluminum also outside.
Yes, yes. This is something generally we think, and the
Hmm.
thing is that since the chamber we are talking about, chamber is somewhat, say, 50, 60 centimeters, like, say, 50 centimeter by 50 centimeter by 50 centimeter around. Okay.
Hmm. Hmm.
And the deposition is happening at a distance of, say, actually it happens at a distance of 5 to 6 centimeter only.
Hmm.
The
Hmm.
wafer. So the molecules don't get adequate, like, they are not scattered. They are generally getting deposited. They are very heavy molecule and they generally get deposited. So some material is certainly wasted. Some material certainly goes to the outer walls and gets out. Okay.
Okay.
But
Okay.
most of the material gets deposited.
Yes. Yes. Okay. Thank you. Thank you.
Got it? Yes.
Yes.
Any other questions? No. So the advantage here is that it is simple and it can be used to achieve very pure materials, because there is no reaction taking place. We already, if you already have a pure material, you will get a pure film. If you take care of some other things, some small things like maintaining a good vacuum and these things, as well as it is low energy process. Like, it is not getting bombarded like the ion implantation. Simply, it is getting deposited. Very, like, we can say a gentle process, very gentle, gently or and delicately getting deposited. So we can even deposit it over some substrate which have some delicate structures. It is not that it will damage the structure. Like in case of ion implantation, if you see, we were saying that it will damage the top surface when we are doping. Okay. But there are at the same time some limitations associated with evaporation, that is step coverage. Since it is getting evaporated, it's not necessary that it will uniformly deposit the whole wafer. It will deposit a small area, and that also center will be thicker, outside will be a bit thinner. Okay. One way to handle this is that we are moving the substrate continuously throughout the deposition. It is uh, moved in circular fashion, and that ensures somewhat uniformity. Anyway, still there will be some non-uniformity in this case. This have some material restrictions, like all materials don't evaporate. Like, they might need so high temperatures that might not be able to evaporate them using such methods, as well as precise ratio is a bit a problem. Suppose that we want to deposit an alloy, the precise amount of mixtures and all, like we want to deposit silver and gold at the same time, suppose, that's a problem. As well as the filament, like suppose we are heating the filament that we are using, that actually can also introduce some contamination, and that is an issue. Okay. Sometimes even laser is used to heat this instead of instead of this what you say, instead of the resistive heating, laser is also used in some cases, but mostly and very commonly, this is one of the most common deposition techniques. Okay. Then comes the second part, that is sputtering in PVD. Okay. To understand sputtering, let's not see this very complex way. It is simply like if we have a mud, we have a uh, pool of mud, and we throw small stones, pebbles on it, and a person is standing there. Okay. If some kids come and throw stones, not on the person but into the mud, what will happen? Anyone? Yes. Any?
Reflections will come, like will
Yes. Yes. Continue. Yeah. Some like some it will sprinkle out some mud over the person. Although what is getting involved is that this person is throwing stones. Okay, and stones remain here and mud comes over the person. Okay, this is the simple method how sputtering works. We use, instead of stone, we use some ionized gases to hit the surface of our target or the material, and that that material gets sputtered to the substrate that we want. Okay, and the ionized gas that we use is the most common one is the argon. Sometimes combination of some other gases, or like combination with argon, but mostly argon. And why? Because if you see the periodic table, you will see that argon is a heavy material. If you are throwing very small stones in the mud, it might not have any effect. And if you are throwing a big stone, it will just hit and remain there. Nothing will come out. Okay. So we have to maintain that somewhat in the size, able to hit out the materials that we have. And argon is mostly suitable, as well as it will not do any kind of reaction. Okay. So it will cause atoms or cluster of atoms to be ejected from the target surface. So we have a target, say SiO2, using argon ions. Okay, it is getting heated, like it will hit, not heated, it will hit, and it will take out some SiO2 materials with it, and it will deposit over a silicon substrate. Say this is the simple process that is the sputtering. Okay, and they are neutral. These materials are neutral. Argon, it will get like it will get ionized. It will work in the transportation of the material and again become neutralized. After that, again using plasma, argon plasma we create, and it will again be ionized, and this process will continue. Okay. In this case, like in CVD, we were giving the energy through heaters, pure temperature. Okay. In case of evaporation, thermal evaporation, we are mostly using current. We were giving energy in form of uh, still in form of temperature. But here the energy is not provided in form of temperature, but is provided electrically, either through DC or RF, to form the plasma, because plasma or the ionic form of argon plays the role here in the deposition. Okay, this is suitable for metal, dielectric, and some semiconductors, where film thickness control is required. Okay, in such cases it can be used. So here are some common the slide have changed. Yeah, here are some of the common ways in which sputtering is done. The basic one, like I said, sputtering gas, this is mostly argon. Okay, this is the target. So this whole system will be connected to like negative and positive. Okay, and as such these ions will move towards the negative. They are positively ionized. They will move towards the target, hit it, and take out the material towards the positive ion. And here, like in this whole process, this material will not get ionized. It will just change the phase. Like it will move with the plasma towards the substrate. Simple. Then a modification is there where we are saying magnetron sputtering. Okay. In this case, magnetic field is added along with this, and this enhances the what you say enhances the sputtering. Then this one is a basic DC system. This is magnetron system, and another one is an RF system where radio frequency of certain frequency is maintained to sustain the plasma, and this is especially useful where we have dielectric non-metallic materials. Okay, below I have shown one of the systems that we use in our lab. Okay, if you see this, this area is the area where deposition occurs. This not this, yeah, this other one is the load lock chamber where we are putting the sample, and because we cannot break the vacuum every time, and we are like, so we have a small chamber attached to it. We are putting the wafer and other substrates there, and then moving through this uh, magnetically controlled arm, moving inside the vacuum chamber. And here this blue parts you see, they are connected inside to the target. We have different, like suppose copper, aluminum, as well as SiO2, silicon nitride. There can be other, and then they are powered through. We have both the system, DC as well as RF systems. Okay, so upper one, this is uh, RF system, and below we have a DC system. Okay, according to our use, as well as this we call as gun. They have magnetic field. So what we have is a combination of this, like magnetron and RF sputtering. We can use both magnetron as well as RF sputtering for our purpose. Okay, so yeah, yeah. Okay. Before going to magnetron sputtering, let's talk about the yield. Okay, so what is the sputtering yield? So it is the ratio of ejected target atoms to the incoming argon ion, and it depends on the type of the inert gas being used. Argon, and in sometimes neon, in some cases neon is also used. Okay, and the target material. So it is in a sense ratio. Okay, as as we move towards some heavier gas, as I said, argon is heavy from most of the materials that we are using. But if we are going for some even heavier gases like neon and xenon, okay, in that case we will get higher yield. But the problem is that they are much costlier. So in the, like in the list of noble gases, argon is the one we can easily get. Okay. What are the factors that define our yield? One is target material. Like if we have some lighter material like aluminum, we'll have higher yield. If we have heavier material like silver or gold, we will get lower yield. Okay. Then there is another thing, that is angle of incidence. So we saw that although it looked like the wafer and target are kept like that. Okay. But it is not necessary to be kept like this. As well as the ions that come, they will not hit like this. They might be hitting at some angles. Okay. This angle of incidence will also like affect our yield, and that and as 60-degree is considered as the optimal yield angle, that's why in this in the system that you were seeing in our case also, we don't have a straight, we have an angle between the substrate and the target. So it is not like parallel, not 180 degree to each other. They are at some angle to each other. In our case, I think it is between 45 to 50 degrees. It is slanted at some angle. Okay. And it will also depend on the plasma formation. This is plasma is where when we apply the very high field. Here also we are talking about very high field, but the current used is much less. The power and the current used is much less compared to what one we were using in case of thermal evaporation. But here the complexity of the system is much higher compared to the one we use in case of thermal evaporation. Okay, so it requires a sufficient number of energetic electrons for the ionization to occur. Okay, uh, so that a self-sustaining plasma is there. Otherwise, we will have to pump the like keep giving a lot of electric current for it to work. If a self so it requires adequate number of energetic electrons, and that is provided from the DC or RF source, and the plasma will also depend on the product of the electrode distance and the gas pressure. So unlike the one we were talking about in case of thermal evaporation, here what we do is that first we create a very high vacuum, like inside everything will take out, then we insert the argon gas. Okay, and when we insert the argon gas, the the pressure will at first we reach, suppose, a pressure of 3 into 10 to the power minus 6 millibar. Okay, and then what we will do is that we will okay, so yeah, as yeah, we will have 3 into 10 to the power minus 6 millibar say, and then once we have reached this, the pump will remain on, and we will insert some amount of gas. We will close the outlet, like we will decrease, and we will sustain a pressure, say 4 into 10 to the power minus 2 millibar, or say minus 3 millibar. And why is this so? Because we need enough gas pressure for the ionization and for the plasma to happen. Sometimes for specific cases, this can happen at minus 2 range, or even sometimes the plasma will form in minus 3 range. It will depend on our purpose. And the plasma formation is dependent on the product of electrode distance, that is positive, negative, and generally its target and the substrate and the gas pressure. Okay. Then we have to increase the yield, we have something called as magnetron sputtering. Okay. So how it works is that it uses magnets, very strong magnets. I think one magnet I had once, one that got actually damaged after it, after being used for long. Okay, and that also is too strong to, like, two magnet I cannot remove. It's like that. Okay, so very strong neodymium magnets are used to confine electrons close to the target, and as such the plasma will be more towards the target, so a lot of ions will easily hit the target, as well as uh, this will actually ensure that we are not putting too much of gas to increase this. Okay, uh, like, otherwise to increase the amount of ions hitting the target we will have to increase the gas pressure, but we don't want to increase the gas pressure because after a limit there will be collisions, a lot of collisions will also be there. So to counter that, to maintain the mean free path, we have uh, magnetron sputtering, in which magnetic field is used to assist the plasma and to increase the plasma density around the target, and as such enhancing the sputtering. Okay. Electron follows the spiral path due to magnetic field, and as such if you take out the target, you will see specific patterns, like if this is a target. Okay, after like you started with a blank target plane, after depositing for some time you will see in the center the material is intact, then around ring kind of structures will form in magnetron sputtering, because the path forms like that, and because magnets are kept like this, and the path forms a ring kind of structure. Okay, as well as argon ions remain largely unaffected due to their heavy mass, and as such their path is not, like, though the density increases, the plasma increases, but their path is not affected. As such the deposition rate is highly enhanced in case of magnetron sputtering, around even around 1000 nanometer per minute. Okay, this can, so it can be very fast, that is 1 micron per minute deposition can even be done using magnetron sputtering. Then there is another way, that is this DC or magnetron sputtering is mostly used for metal, because we are saying that the target itself is an electrode. But what if we have to deposit some non-conductive targets like oxides, nitrides, because charge will build up due to the capacitive effect. So an AC bias of 13.5 megahertz is used to create the plasma. Okay, and as such, since the field is fluctuating, positive, negative, is AC, the charge accumulation on the target will not happen. There are some frequency consideration, like at low frequency, both ions and electrons react to oscillating voltage, and at higher frequencies, above 1 megahertz, only electrons respond to controlled sputtering. And here, electron has no role, only ions are there. Okay, and that's why a frequency higher than 1 megahertz is taken for the RF sputtering. Okay. With RF sputtering, the advantage is that it can be used for a wide range of material, even metals and non-metals. So we have This RF sputtering can be used for both of these, okay, without surface charging. But if we compare RF sputtering and DC sputtering or DC magnetron sputtering, the quality of film for a metal especially in case of DC sputtering is better compared to RF sputtering. So why we are using RF sputtering? First is for insulating targets as well as to prevent charge buildup. Okay. Now, when we have an oscillating field, these electrons are small enough to follow these oscillations, but argon is too inert and too large to follow this oscillation along with the changing frequency. Due to this, what happens is that a DC potential is formed in the plasma. Even though AC is used, but a DC potential is induced in the plasma due to the nature of argon not to not to move along with the changing AC frequency. Okay, as well as there is one problem that we cannot have, like suppose that we are going to deposit over a 4-inch wafer, so we cannot have a 4-inch target of say gold. That will be too costly. Okay, so we are using 1-inch or 2-inch, so there is a difference. So say negative bias is being applied over a larger area compared to positive bias. I'm saying opposite. Yeah, positive bias is kept over a larger area compared to smaller target area, and as such, this creates a large voltage drop over the target. This actually creates a difference, like a voltage difference, and as such, a DC bias is induced from the RF due to this difference. Like when this movement is occurring, argon first tends not to move or not to oscillate along with this RF, whereas electrons move, and there is difference in one electrode, the area is larger, other electrode, the area is smaller. As such, a DC bias is formed and the plasma is induced. And so without using DC, we are creating a DC kind of effect, and like direct current kind of effect, and we are getting the plasma required, and the argon ions are formed and they hit the target. So what is the energy source in sputtering? Like in CVD, the energy source was temperature. In ALD, the energy source was plasma. In case of thermal, the energy source was again temperature, but in sense of resistive heating. Okay. In this case, the energy is not plasma, neither the temperature. The energy is due to the argon bombardment. How uh, well the argon bombards, like argon atoms are coming in and it is bombarding on the surface. And this bombardment on both target as well as substrate, this is the energy source due to which the sputtering occurs. And this energy is typically in the range of 20 electron volt. So, and this energy can further be increased. If we are talking about RF, it can further be increased by using, along with RF, use DC, a combination of both. Okay. Then once this whole process is done, argon atom is again ejected from the target and it is in the neutral form. And it have still energies between 2 to 20 electron volt. If we are going for very high energy ions, then it can be used to improve film crystallinity and density. So sputtering pressure, like at what pressure? Because these will have more energy based on the pressure, the uh, partial pressure or the gaseous pressure of the argon. Okay, and that will have an effect on the energy of the ejectant atom, influencing the, and this will also influence the film morphology. Okay, if we compare it with the evaporation, this is having more energy than the evaporation, and that is why certainly it will have some surface defects more compared to thermal evaporation, but it will create more dense and more crystalline films, and that is why this is sputtering techniques are even used to create some uh, nanostructures. Like you will see sometimes people are making nano flowers, nano rods using sputtering, optimizing the parameters at some specific parameter, like at specific energy, as well as specific gas pressure. They are able to make different structures, nanostructures, and all. And this is due to the crystallinity, and that is due to the energy that is carried with these materials. Okay. Then this can even be used for alloy and like alloys and reactive sputtering. Okay. Here, uh, the ratio control is very good. Okay. Sometimes, if you are depositing silicon nitride or something, sometimes, though we are talking about sputtering PVD, sometimes we have to put some reactive gases, okay, into the sputtering chamber. So so it is like PVD, but a bit of chemical reaction is also taking place. So this is called as reactive sputtering, and this is sometimes done for silicon Si3 and 4. Like we have like we are introducing nitrogen along with the argon for the nitridation of our silicon oxide, and there the reaction is also taking place. This is called as reactive sputtering. Even alloys can be deposited like nichrome using sputtering. Okay, it has a wide application for depositing metal oxides, nitrides, carbide, and other compound materials also. Fine. So, okay. So the advantage is, uh, yeah. Am I audible?
Yes,
Yes,
yes.
Yeah.
yes.
Everyone getting right. So the advantage with sputtering is that it allows for uniform deposition over large areas. Okay. Unlike the evaporation, where the deposition is not uniform. But in case of sputtering, if we rotate the substrate perfectly, uh, the thickness is almost same throughout the wafer. The change is less, very less. Okay. It has better alloy and stoichiometry control. So alloys also maintain the whatever is the composition of the target, the uh, same thing will be on the deposited like after deposition, right? Because it is a low temperature, like it is not a lot of temperature is not being given like the evaporation. So there, if we were mixing an alloy, it might become something else when getting deposited. As well as in this whole process, there is plasma which actually cleans the surface before starting. Actually, we have seen that plasma cleaning is a process where wafers are cleaned. So before the starting of deposition itself, plasma cleaning in a way occurs, and in situ cleaning up happens. It has better step coverage, not like ALD, but it has step coverage better than evaporation. Okay. Then there are some certainly some disadvantages also. One is lower deposition rate. uh, yeah, lower deposition rate. Okay. Then since it is carrying a lot of energy, it can potentially create damage to soft materials. Okay. It has no, it has a higher impurity level. Like I said, although we are going to lower pressures, okay, that is very high vacuum, but the real operation occurs at a higher pressure, say 10 to the power minus 2, minus 3 range. Okay, that's why there can be impurity levels higher compared to an evaporated sample or thin film. The equipments are much complex compared to thermal evaporation. In thermal evaporation, it is simply a transformer to step up the current, and we get the and we have boat and all, and pressure systems, like vacuum systems. Whereas in case of sputtering, we have DC, RF, magnetron, lot of complex things, and that has to be controlled very precisely. Along with that, the whole system has to be properly cooled, because this whole process uh, generates a lot of heat. Continuous flow of water or coolant is to be done, and such things, like it makes the equipment complex, very complex for operation. Okay. So any questions still here?
No, clear.
No, thank you. No.
Yeah. So I have put some questions. I will be putting this in the like I will be posting this. Along with that, I have put the explanation of each of these questions. If you see, okay, uh, okay, this has become a bit crowded. Yeah. So I have put all the explanations. You check through this, uh, okay, and if any questions, like there are any doubt, these are something that we have discussed. Most of the things has been discussed. Okay, like at what pressure range is the evaporation process typically carried out to ensure efficient deposition and minimal contamination? Yes. So what will be the answer? Okay, answer came. Yeah, there is some lag and delay. Yeah. Yes.
Ultra high,
Ultra high vacuum or high vacuum. Ultra high
vacuum.
vacuum.
Yeah,
Yeah.
ultra high vacuum is for the image for characterization only.
Yeah, for
For
to
high vacuum.
characterization. Yeah, these things are used. Ultra high vacuum is used in case of TEM and these things. Okay, so like most of these we have covered. Anyway, even if there is still anything that you are not able to understand or any confusion, we can you can just write to me, or we will be discussing in the next class. Fine.
Okay, fine.
Yeah. So any other questions? Anything related to this class?
No, thank
No,
you.
No.
Thank you
no.
very much.
Thank you. It was really great
Okay.
lecture. Thank you.
Thank you. Thank you, everyone.
Thank you. Thank you. Thank you.
Yeah.